Hi guys, great to be back with you. And remember, today we're doing with physical science and we're doing paper 2. So chemistry, let's get cooking with chemistry. Before we carry on with chemistry, I want to remind you, we're trying to focus on the prelim papers. Now, we've got the GDE prelim paper, the one from Gauteng, and the provincial paper from KZN. If you've got any other questions, though, please send them through, post them on Facebook, send them via email. The email address is helpdesk@learnextra.co.za. Of course, you can also phone us directly, 086 1058 262, and we'll get your questions down, we'll get your call, and we'll pass you through to the studio so that I can help you with your particular questions on paper 2. Now, we're going to start by looking at chemical equilibrium. I know this is a section that a lot of you battle with, so let's get straight into it. And the first question I want to deal with is a short question from the KZN paper. It is or the GDE at least, and we're going to take a look at it because it's an interesting question in terms of the application. So here it is. It's question 210, and here we go. It says the following hypothetical. Now, hypothetical means that it's not real. It's just a model. We don't have to get too worried about it. Is at equilibrium. So the hypothetical reaction is at equilibrium at 620 K. Remember, K stands for Kelvin. That's the temperature. So we've been given a clue. We have a certain temperature, and that looks quite a high temperature to me. And we're told this is the reaction. We've got the reactant, 2AB2 gas plus B2 gas goes to form 2AB3, which is also a gas. And we recognize it's an equilibrium because we've got a forward reaction and a reverse reaction arrow there. It tells us the diagram below shows the molecules. It's just a sample of the molecules involved in this chemical equilibrium at 620 K. The white circles, now we want to remember this, so we're going to take a note of it. The white circles are A, and now because I'm dealing with black over here, I'm going to say this, the white circle is A, and let's have a look what they say. B is the black circle. So this one is going to represent B. The colored one, the one that's black, that's B. So let's recognize what we've got here. This is B2. This means that this is 2B and an A. So that's A, B2. That's another B2. This is an AB2, and this is an AB2, right? This is another AB2, and here we've got 3 Bs and 1 A, so this is an AB3. So let's just count up, because I know that we're going to need this just now, so let's just count up so that we've got the right ratios all sorted out before we carry on. Of B2, how many have we got? Well, there's 1, and I'm going to score it. That's 2, and I think I've got 2 of those. So I've got 2 B2s, and then what about the AB2? I've got 1 over there, I've got another 1 over there, I've got another 1 over there, that's 3 so far, and that one is 4. So AB2 is representing 4, and AB3 I'm representing only 1. Okay? This is the sort of thing that you should be doing as you're reading the question. You need to interpret what you've got and how many you've got, and it does help if you do that. Now it tells you the following. It tells you that the temperature is now decreased to 490 K. So this is lower temperature. And so here's what the mixture looks like again. So we're going to use the same symbols, and let's count up what we've got. Remember, the 2 black ones are B2. The white one and 2 black ones is AB2. And this one has got 3 black, so it's AB3. And this one has got 3 black, so it's AB3. and this one has got 3 black, so it's AB3, and this one has got 2 black and 1 white, so it's AB2. So can you see now what we've got? Let's write it down and compare. So at a lower temperature, we've got B2. We only had one of them. And of the AB2, 1, let's cross it out when we've done it. AB2, there's another one, so that's 2. So we've got 2 of those, but the big difference is of AB3. I think that one is the conclusive one. Let's just check it. We've got one of them there, we've got another one of them there, and we've got a third one over there. So we've clearly got 3 of those. So it now says, from the above, it can be concluded that. Well, let's have a look and do the comparison about what we've got. We started with 2 of these. Let's look at the reaction as well. Let's have a look at that. We said it goes 2 of that to 1 of that to 2 of those. So we know what the reactants are. These are the reactants. Reactant. And this is the product. And what do we see? We started with 1 of these, and we've ended up with 3 of those. So that means, if we look at it, we also recognize we started with 2 of those, we've got 1 of those, we started with 4 of those, we've got 2 of those. So this is decreased, decreased, and this is increased. There's been an increase. So what is that telling us? If we look at the reaction over here, it tells us that the forward reaction has been favored and the reverse reaction hasn't been. It's reached new equilibrium with more product than reactant. The forward reaction has been favored. Now, what we need to do is look at what the questions then say to us. So it's really important to do the analysis, recognize what's happening. We can see more product is forming. That tells us the forward reaction is favored. I hope you've got that by recognizing the reactants have decreased and the product has increased. So the forward reaction is favored. Okay? But now, it doesn't tell you just the forward reaction is favored. It tells you the following. It says, decide. From this we can conclude that the forward reaction is exothermic, the forward reaction is endothermic, the concentration of AB2 is higher at low temperatures, the concentration of B2 is higher at low temperatures. Okay, so let's test each of them. We'll start with number D, and let's see what has happened to B2. The concentration of B2 has decreased, so that one can't be right. What about the concentration of AB2? Well, it's also decreased, so that one can't be right. So now we're left to decide, is the forward reaction endothermic or exothermic, and how are we going to do that? Well, it's not difficult. What we need to recognize is that we have a decrease in temperature. We all recognize that there was a decrease in temperature. It went from, remember, a high temperature of 620 Kelvin to 490. It went from 620 Kelvin to 490 Kelvin. So we know it's been a decrease. Decrease in temperature. Now a decrease in temperature always favors the what? Let's think about it. If you decrease it in temperature, what do you try and do? What does the system do? Le Chatelier's principle. You've provided a stress on the system. You've taken away some temperature. What does the system try to do? It tries to replace the energy. It tries to replace the heat. So if you lower the temperature, what's the system going to do? It's going to try and increase. So it's not going to absorb, it's going to try and release some energy. So a decrease in temperature always favors the exothermic reaction. You try and decrease the temperature, it will try and make more heat. So if you take away heat, it will try and make heat. So it will favor the exothermic reaction if you decrease the temperature. And in this case, we can therefore say we've worked out that therefore the forward reaction was favored. forward reaction, the favored reaction was the forward reaction. So if the forward reaction was favored, we recognize that this is what the system was doing. It was trying to favor the exothermic reaction. So therefore, we can say the forward reaction is exothermic. Right. So which answer was that? Forward reaction is exothermic. The answer is A. Now, I hope you can see how to go through a multiple choice question like this. It's really important that you make sure that you've got your wits about you. Remember Le Chatelier's principle. You're going to be asked it. Make sure you know the statement of Le Chatelier's principle, that in an isolated closed system, that if in chemical equilibrium, if a stress is applied, the system will work to relieve the stress. And so until a new chemical equilibrium is established, make sure you learn your laws and you can apply them. And particularly note that if you've got a change in temperature, it's going to affect the things in the following way. A decrease in temperature is going to favor the exothermic reaction. An increase in temperature is going to favor the endothermic reaction. We also recognize that it's only temperature change that is going to cause a change in Kc value. Okay, let's see what we've got. I think we've got another question that is related to this. So let's pull it up. And we are going to take a look at the KZN questions on Kc that happened in the short questions. Question number 2, and let's see if we can apply this. So it says the following thing. Question number 2.5 says the following. It says the following reversible reaction. So read the question carefully. Reversible reaches equilibrium in a closed container. So all the rules of chemical equilibrium apply. We've got H2 gas plus I2 gas to give you 2HI, and we're told that delta H is less than 0. Do you remember what delta H less than 0 means? Hope so. Means that if it's less than 0, it's a negative. That means that in the way it's been written, it is exothermic. Please make sure you've remembered that. Delta H greater than 0 means it's positive. Okay, it tells us equilibrium was first established after 5 minutes, and there we can see it. Notice that this is a rate of reaction versus time. So it's a really important graph to take note of. Rate of reaction versus time. The rate of the forward reaction, rate of forward equals rate of back or reverse. Okay, and we can see that. Now, what it then says to us, the broken line represents the reverse reaction or the back reaction. What's the question? What change in the conditions were made at 10 minutes? Now look at the graph and let's see. There's the 10 minutes. So we're going to have to interpret that one, although they've given us the 15 minutes as well, and we'll have a look at what happens at 15 so you can explain it. So read the options. Here's another strategy. When you look at the question, read the options first, then do your own calculation. So here it says a catalyst was added, the temperature was increased, the temperature was decreased, the external pressure on the reaction was decreased. So we've got catalyst, temperature, temperature, pressure. Okay, let's go and have a look, analyze the question. There's the data. Let's go and have a careful look at what's happening here. Now, this is the area we're looking at. Notice what's happened at 10 minutes. Here's our point, 10 minutes. We notice that both the forward and reverse reactions have increased, and they've increased by the same amount. Now, the only way that that can happen is if you've added a catalyst. That tells you that you've added a catalyst. An addition of temperature will increase one of them more than the other. Yes, they will both increase. One of them more than the other, though. Remember, which one's going to increase more? Well, we recognize that if you increase the temperature, you're going to favor the endothermic reaction. So the endothermic reaction will increase. The exothermic reaction will increase as well. The endothermic reaction will increase more. So we recognize it's not temperature. It's not a change in addition of a substance, because then one will be more than the other. So it's not addition of a change in concentration. It's not a change in pressure, because pressure will not have any effect here. Because look, if we change the pressure, have a look, it might change the rate a little bit, but it's not going to shift the equilibrium. So we recognize we've got 2 moles here, we've got 2 moles there. Pressure is not going to have an impact. The external pressure on the reaction was decreased. No, decreasing will actually slow it down. So it can't be pressure. If it was increased, maybe it would increase but it was decreased. So it can't be pressure. So we recognize 2 moles to 2 moles, not going to cause a shift. Increasing the pressure might have increased but it's not an increase, it's a decrease in pressure. So the only one that we're left with is a catalyst. So for this question, the answer was A. But let's have a look at what happens at 15 minutes, because I think that's the more interesting thing that happens. So what do you think is happening at 15 minutes? Let's have a look at it. Notice, first of all, what we need to recognize is that the rate of the forward rate decreases. Okay? And it's decreasing. This rate here of the back reaction decreases as well, but it decreases, and then increases. And then increases. So let's have a look at seeing what's happening here. So we recognize the forward reaction is endothermic. The reverse reaction, the forward reaction is exothermic. The reverse reaction is endothermic. So what we've got is the reverse reaction here is endothermic. So what's happening? We've got a decrease in the forward reaction. We've got an increase, a decrease in the reverse reaction as well. Now, when they both are changing, they're both decreasing, then I would have suspected that this is a temperature change. And what we can see here is that this one decreases more. So the forward reaction is decreasing more. And that makes sense in the sense that if we're decreasing, then what we would expect here, this being exothermic, then we're going to cool it down. We should actually change the rate to a certain extent. This rate is still higher than the reverse one. So it looks to me like this is a temperature change. Although there might be a problem with the way that this has been drawn, I'm not exactly sure, but let's just recognize that when both of them decrease, they've decreased at different times. If it was a change in temperature, we're going to expect a decrease in temperature is going to cause both rates to slow down. If we decrease the concentration of one of the substances, it's not necessarily going to change the rate of reaction of both of them. So I would suggest that maybe this is a temperature change, but it is an interesting thing to go and analyze. Check with your mates and have a look at it. Let's move on to the next question. 2.6. 2.6. The graph below represents a change in potential energy for the following reaction. So it says A2 plus 2B2 gives you 2A-B2. Okay? So we recognize these are the reactants. And this is the product. Notice it's in equilibrium, and we're giving this graph. Now, read the questions. It says, which one of the following statements is correct? The forward reaction is exothermic. The heat of reaction for the forward reaction is Q minus P. the activation energy for the forward reaction is R minus Q, and the activation energy for the reverse reaction is R minus P. So have a look and let's apply them. Let's start with number D, the activation energy for the reverse reaction. Now, the activation energy for the reverse reaction would be that. That's the activation energy for the reverse. So if we were to do it, we're wanting to work out the energy, we'd recognize that it's R, that energy difference, minus Q. So if we go back here, it's not R minus P, so that one's wrong. Now, let's have a look. The activation energy for the forward reaction. Activation energy for the forward reaction. We start with the final reaction, which is R, minus the initial, minus P, and that would be the activation energy for the forward reaction. So what do we say? It is R minus P. So that one is also wrong, not the correct one. The heat of reaction for the forward reaction. Now, remember, delta H for the forward reaction or for the reverse reaction are the same magnitude. They're just different sign, but we'll have to look and see exactly what it's saying. So if we were looking for the delta H value for the forward reaction, we're going to say the product is going to be Q. That's where the energy is, minus P. So product minus the product being Q, minus the initial. Notice that this is a higher energy, this is a lower energy. You're going to get a positive value. So we've got Q minus P. And check, that's the correct answer, the same answer as B. So it looks like B could be correct. Now, let's just have a look at A to make sure that it's not correct. It says it's exothermic. So what does exothermic mean? Notice here, this means that delta H is greater than 0. Exothermic means that delta H must be less than 0, must be a negative value. The graph that you get would look like that. That's the shape of the graph for the exothermic reaction if it was forward. Over here, products have more energy than the reactants. This is endothermic. Okay, so it's clearly not A, so B is your right answer. Okay, well, I hope that those short questions on rates and chemical equilibrium have got you started to think about the areas that you need to focus on. We're going to go to a short break. After the break, I'm going to do one KC question, but if you've got any other questions, remember, please phone us, 086 1058 262. You can also email your questions to helpdesk@learnextra with an x.co.za, or you can get us on Facebook, and that's the Learn Extra page on Facebook. It's www.facebook.com/learnextra. We'll be back in a few minutes. And remember, I'm supporting you. That's why I'm wearing this jersey. Class of 2011, you go, you make us proud, and we're here to support you. We'll see you after the break.